All right, this is going to be our walkthrough for the assignment titled Functions to Graph. So we've got 9 different functions here that we're going to graph. We're going to try and do as much work as we can without a calculator. You'll note at the bottom I've said, show the algebraic steps, use exact terms. You can approximate using a calculator to plot the point, but label the point with the exact term if you can find it. I'm not going to go through all the arithmetic in all of these, and there is going to be a time or two where I do use a calculator to find a point. I think only just once in the first question. That won't be the case on the test. And on the test, you should be able to find everything by hand, no problem. I may give you some approximations of roots or values of e to help you to plot points and graph them. But other than that, you should be able to do everything by hand. So what we're going to do for each thing first is find the x and the y intercepts, steps 1 and 2. And then we're going to do step 5 actually next, find all the asymptotes, all the stuff we can do without a derivative. And then we'll do the maxima and minima and the increasing and decreasing. And then we'll do the points of inflection and the concave up, concave down. And in the beginning, we'll also think about the domain and the range of our function. So we got a lot of things that we need to do here for this. So let's take a look. Let's get started. The first problem here is f of x equals 3x to the 5th minus 5x cubed plus 3. Now this function, this is the point where I was saying, well, unfortunately, this one we're going to have to use the calculator to find the x-intercept. So I'm just going to tell you for this one, the x-intercept on this is approximately equal to negative 1.419,865, 0. But we can find our y-intercept, or we find our y-intercept by evaluating f of 0. Right, so f of 0 is just equal to 3, so our y-intercept is going to be 0, 3. So we're definitely going to plot that point 0, 3, and we're going to plot the point 1.419865, negative 1.419865, 0. So I think we'll just make every 2 spaces 1 this time. So 0, 3 is going to be right here, and negative 1.4 should be right around there. Just in the interest of saving space on my graph, I'm not going to label the points on my graph. I did ask you to do that in the assignment. You can see in the answer key I've done that, but that's going to make it a little bit too difficult for me because I don't have as much space as I would if I had a full sheet of paper for the graph. Next thing we'll do is think about asymptotes. This is a polynomial. So polynomials have no asymptotes. So done with the polynomial asymptote part of it. Right? No asymptotes. Next thing to think about would be the domain and the range. Now the domain here is going to be all real numbers, right? Negative infinity to infinity. We can plug anything into this. And the range is going to be the same, right? 5th degree functions with a positive leading coefficient start down here and end up here. Whether there's, maxima and minima in the middle, regardless, it still goes all the way from negative infinity to infinity. So there's our domain and our range. So now we need to go find a bunch more points. So what we'll do is we'll start by taking our derivative. So our derivative of this function, right, since the original function was f of x equals x to the, or 3x to the 5th minus 5x to the 3rd plus 3, the first derivative is going to be 15x to the 4th minus 15x squared. That's never going to be undefined, but we'll set it equal to 0 and take out the 15x squared, leaving us with x squared minus 1, or factoring it completely, giving us 15x squared times x plus 1 times x minus 1 equals 0. There are 3 critical values, x equals 0, x equals negative 1, and x equals positive 1. We'll put all 3 of those on a sign chart to determine how the function is behaving. So we'll do that over here. Here's negative 1, 0, and 1, and this is f prime that we're evaluating this at. So if we put in something like a million, all 3 pieces of this are going to be positive, so we end up with a positive. If we put in something like a half, the first term is positive, the second term is positive, but the third term is negative, giving us a negative. If we put in something like negative a half, the first term is positive. The second term is also positive, but the third term is still negative, so it's still negative. And then if we put in something less than -1, like -1,000,000, we get a positive for the first term, but 2 negatives here, leading to a positive, telling us that f increases, then decreases across that whole interval, and then increases again. Right? That's what f is doing. We will need to then find what f of 1 and f of -1 are. So I'm not going to go through the arithmetic of it. F of 1 is just going to come out to be, f of 1 is just 1, and f of -1 ends up being 5. So we've got a local max of 5 at x equals -1, and we've got a local min of 1 at x equals +1. We are increasing on the interval from -infinity to -1, and then again from 1 to infinity, and we are decreasing on the interval from -1 to 1. So we need to put the points -1, 5, and 1, 1 on our graph. So -1, 5 will be right here, and 1, 1 will be right here. And then we'll, I believe it asked us to, actually it didn't ask to identify absolute maxima or minima, so we don't have to worry about that. But neither of those are absolute maxes or mins anyway, because we're going up to infinity and down to -infinity. So now we'll take our second derivative. So f prime of x was equal to 15x to the 4th minus 15x squared. So f double prime of x will be 60x cubed minus 30x, which will set equal to 0. Factor out of 30x, leaving us with 2x squared minus 1 is equal to 0. And so that gives us x equals 0 and x equals positive or negative 1 over root 2 when you solve that out. So we have 3 possible points of inflection, and we will evaluate our second derivative at all of those places. So we've got -1 over root 2, 0, and 1 over root 2, or not at those places, but at the intervals between those. So something more than 1 over root 2, like a billion, is going to make both of those things positive. We concave up. Something between 0 and 1 over root 2, well, something between 0 and 1 over root 2 is certainly positive. It makes 30x positive, but it makes 2x squared minus 1 negative, so we're going to have a negative in there. And then something between -1 over root 2 and 0 still makes the 2x squared minus 1 negative, but now it also makes 30x negative, so that becomes positive. And then anything below -1 over root 2 makes it a negative for the 30x, but a positive for the 2x squared minus 1, and so we have a negative. So our function has 3 points of inflection, right? It switches from concave up to concave down 3 times, and we'll state that it's concave down on the interval from -infinity to -1 over root 2, and then again from 0 to 1 over root 2, and it's concave up on the intervals from -1 over root 2 to 0 and 1 over root 2 to infinity. And then we already have the point at x equals 0. We knew that that point was 0, 3. And so that's one of our points of inflection. Okay. And our other points of inflection come from evaluating the original function at -1 over root 2 and +1 over root 2. I'm not going to go through the arithmetic on that. I won't give you arithmetic that's that annoying to do on the test. So -1 over root 2 came out to be 24 plus 7 root 2 over 8. Right? And +1 over root 2 came out to be 24 minus 7 root 2 over 8. And again, I'm not going to do the arithmetic. You can do that on your own if you want. those values approximate out to be, let's see, the first one here, the 24 plus 7 root 2, that one comes out to be about 4.237, and this one comes out to be about 1.7625. 256. And so when I plot those points, that should give me enough information to finish graphing it. So at -1 over root 2, which is a little bit to the left of -1, we're up at about, it was 4.2, right? So we'll be, let's see, 4.2, somewhere around there. And then for the other one, we will be at around 1.7. So 1.7 should be right around there. And we will then sketch our graph, knowing that we start out increasing and concave down, right? Until we get to that first point of inflection, we're going to stay concave down, and we're going to stay increasing until -1 and then start decreasing after that. So we're going to be concave down, and that's not good. We're going to be concave down and increasing, then concave down and decreasing. Then we're going to switch to concave up and decrease. Then we're going to switch to concave down and decrease. Then we're going to switch back to concave up and decrease. Then we're going to stay concave up and increase. And that's what our first graph should look like. All right, our second one here, we are going to first start off with the x and the y intercepts, right? So our x and our y intercepts here should be just set equal to 0 here. Cube root of x squared should equal 0, and 3 minus 2 cube roots of x should equal 0. So this gives us x equals 0, and this gives us the cube root of x equals 3/2, which means that x is equal to 27/8. So we've got two x-intercepts, 0, 0, and 27/8, 0. Then we also have a y-intercept. We don't need to do any work to find that. The y-intercept is just 0, 0. Right? And we should recognize that I can plug anything into this. Right? Our domain is going to be all real numbers. We should recognize that there's not going to be any vertical asymptotes because there's no discontinuities. And there's not going to be any slant asymptotes because this is not a rational function. We could have horizontal asymptotes. So we should look at what the limit as x approaches infinity is and what the limit as x approaches negative infinity is. So the limit as x approaches infinity is going to end up being negative infinity, right? Because we end up with a positive infinity times 3 minus infinity, which is negative infinity. And then we do a limit as x approaches negative infinity of f of x, which gives us, again, an infinity, because negative infinity squared is positive infinity, and if we cube root it, it's still positive infinity, over 3, or times 3 plus infinity, which is infinity. So our range, we're going all the way down to negative infinity, all the way up to positive infinity. Our range is negative infinity to infinity. We knew there was no slant asymptotes. We knew there were no vertical asymptotes. These two limits tell us that there are no horizontal asymptotes, so we will just state that there are no asymptotes at all for this function. I'm going to space this out a little bit so that like each 2 is going to be 1 here. And so I have a point at 0, 0 and a point at 27/8. Well, 27/8 is about 3 3/8, so that'll be right about there. So that's all I can do without taking a derivative of this function. So we'll start now with our first derivative. So we had the cube root of x squared times 3 minus 2 cube roots of x. That was what f of x equaled. I don't want to take the derivative in that form. I'm going to distribute this out first. So cube root of x squared is x to the 2/3. So that's going to be 3x to the 2/3. And then when I multiply x to the 2/3 by x to the 1/3, that just becomes x to the 3/3 when we add the exponents, or just x to the first power. So minus 2x. So when we take our derivative, f prime of x, we should end up getting just the derivative of 3x to the 2/3 should just be 2x to the negative 1/3, and then minus 2. Okay? And so we'll rewrite this as 2 over the cube root of x minus 2. Getting ourselves a common denominator of cube root of x will help us to determine when this is undefined and when it equals 0. So we'll rewrite our derivative as 2 minus 2 cube roots of x over the cube root of x. Well, that's undefined if x equals 0. So there's one critical value. And it equals 0 if the numerator equals 0, which would be when the cube root of x is equal to 1, or when x is 1. So we have two critical values. We have 0 and we have 1. And if we test some values here, if we plug something like 1,000,000 in, the numerator is definitely going to come out to be negative, and the denominator is going to be positive. Right? So that'll be a negative, which means the function is going to decrease. If we plug in something like a half, or actually let's plug in an 8, right? We can do 2 minus 2 times the cube root of an 8, which comes out to be just 1 is positive, and the cube root of an 8 is positive, so that's positive in the middle. And if you plug in a negative number, then we're going to end up with a positive in the numerator, but a negative in the denominator, which gives us a negative, telling us that this function decreases, then increases, then decreases. We're going to have a local min at 0 and a local max at 1. We need to find f of 1. Well, if we plug f of 1 in, plug 1 into f of x, we just get 1. So we've got a local min of 0 at x equals 0, because we already found that point. We've got a local max of 1 at x equals 1. And we are increasing from 0 to 1 and decreasing from negative infinity to 0. And then again from 1 to infinity. And we'll plot that point 1, 1 on our graph. And then we'll go right ahead and find our second derivative using our first derivative form here, 2x to the negative 1/3 minus 2. So if f prime was 2x to the negative 1/3 minus 2, right, then the second derivative of this should just be negative 2/3 x to the negative 4/3, or negative 2 over 3x to the 4/3. This is never equal to 0 because the numerator doesn't have a variable in it, right? And so we can't make it equal to 0. But we can see when it's undefined. It's undefined if x is 0. Well, if x is 0, we know we're not going to have a point of inflection because we already had a local minimum at 0. But we'll still make the sign chart just to make sure we didn't make a mistake maybe before. And if we plug in a positive number or a negative number to x to the 4/3, we're going to raise that number to a power of 4, which is going to make any input a positive. So we're going to have a positive in the denominator, and we're going to do negative 2 divided by that, which is going to give us negatives for both of those. And so we'll say that this is concave up, never, and it has no points of inflection. And it is concave down on the interval negative infinity to 0, and again from 0 to infinity. If you wrote negative infinity to infinity, I might have even done that on the answer key, that's okay. But really, its second derivative is undefined at 0, so it's not concave up or concave down at 0. So this is really a more accurate representation. But now we have no new points to plot, so we're ready to just graph. We're concave down, coming from infinity to this minimum. Then we're still concave down, going to the maximum. Then we're still concave down, but decreasing down to negative infinity. And so that's what our graph should end up looking like. All right, our next one here is x times the square root of 9 minus x squared. So we'll start off by thinking about the domain of this function, right? 9 minus x squared needs to be greater than or equal to, or not greater than, yeah, it needs to be greater than or equal to 0, right? Which means that 3 minus x times 3 plus x needs to be greater than or equal to 0, which means that my cutoff points here are going to be 3 and negative 3. So I'm going to make a sign chart with my function, with just that 9 minus x squared part of my function, to see when this is actually positive. So if I plug in something between negative 3 and 3, like 0, we end up with 2 positives, which is positive. But if I plug in something more than 3, like 1,000,000, I end up with a negative times a positive. Or negative 1,000,000, I end up with a positive times a negative. So our domain here is just going to be restricted to the values from negative 3 to 3. Right? So that's our domain. Any critical values we might find have to be on that domain. So now we'll look for our x and our y intercepts. So we'll start with x intercepts. That'll be when this is equal to 0. Well, we just found that the root 9 minus x squared part equals 0 when x is 3 and negative 3. So that's 2 x intercepts, 3, 0, and negative 3, 0. And then also, f of x equals 0 if x equals 0. So that'll be a third x intercept. And it also happens to be the y-intercept, right? Because y-intercept of 0, 0 will always match up when you have an x-intercept of 0, 0. So we'll plot those points. I think I'll make each box, each 2 boxes 1 again. So at negative 3, 0, we have 1. At 3, 0, we have 1. And at 0, 0, we have 1. And so we will then kind of think about, well, we'll figure out our range later on. We'll think about horizontal asymptotes. Well, that's just not even a possibility, right? Because we're not even going towards infinity, right? As x goes towards infinity or negative infinity, this function doesn't exist. So there's no horizontal asymptotes. It's not a rational function, so there's no slant asymptotes. And there's no discontinuities because we have these like actual endpoints, right? We don't have an open interval at the end, so there's not going to be any vertical asymptotes either. So we don't have any asymptotes. So no asymptotes whatsoever. So now we're ready to move on and do the derivative portion of this. So we will start with our function f of x is x root 9 minus x squared, and then we'll take the derivative of that. And of course, to find the derivative of this, we're going to have to use the product rule, right? So we'll start off with, f prime of x is equal to the first function, x, times the derivative of root 9 minus x squared, which is 1 over 2 root 9 minus x squared, and then times the derivative of the 9 minus x squared, which is negative 2x. And then we'll add to that the derivative of x, which is 1, times root 9 minus x squared. We'll want to cancel out our 2's, because that'll just make getting a common denominator a little bit easier. So we'll multiply by root 9 minus x squared over root 9 minus x squared here to get our common denominator. That's going to leave us with a negative x squared plus 9 minus x squared over root 9 minus x squared, or negative 2x squared plus 9 over root 9 minus x squared. I don't really need to worry about what makes this undefined. That'd be a positive or negative 3. Those are my endpoints. Right, so I know I'm going to have a max or a min at those endpoints, and I know they need to go onto my sign chart. So really, I'm just going to focus more on what makes this equal to 0, which would be when negative 2x squared plus 9 equals 0, or when x squared is equal to 9/2, which of course gives us x equals plus or minus 3 over root 2. Okay, so we got two different values here that we're going to put on our sign chart, and our sign chart is also going to include -3 and 3, and here's -3 over root 2, and here's +3 over root 2. And so if I put something in the middle into that, like 0, we're going to get a positive in the numerator, and the denominator is always going to be positive, right? So we're going to have positive there. And then if I put in something between, let's say between -3 and -3 over root 2, well, we know that those values are what's going to make the numerator negative, and the denominator is still going to be positive, so we'll have a negative. And the same with 3 over root 2 to 3, right? If I put like 2.9 in there, I'm going to have a negative in the numerator and a positive in the denominator, which means my function f is going to go from decreasing to increasing to decreasing, meaning that I need to know the value of my function at -3 over root 2 and +3 over root 2 so that I can find the values of those local maxes and local mins, which in fact will end up being our absolute maxes and our absolute mins. We'll see in a second. So I'm not going to do the arithmetic again. F of -3 over root 2. Right? F of -3 over root 2 is just -9/2. And f of 3 over root 2, you can plug it into the original function, and you end up getting +9/2. So that tells us that we've got a local and absolute also maximum of 9/2 and a local or absolute minimum of -9/2. So we'll write out the information about our first derivative, right? So we've got the local, and we'll even say local and absolute. It was a local absolute max of 9/2 at x equals root 3 over 2. Sorry, 3 over root 2. And it's a local absolute min of -9/2 at x equals -3 over root 2. And we actually, if we think about this too with our sign chart, we've got a local max at -3 and a local min at 3, right? Because those are our endpoints. So we're going to say we have a local max of 0 at x equals -3 and a local min of 0 at x equals +3. And our function is increasing in between -3 over root 2 to +3 over root 2. And it was decreasing from -3 to -3 over root 2, as well as from 3 over root 2 to 3. And we'll need to plug in those points at 9/2, or the y values of 9/2 at 3 over root 2. So we'll plug those in. 3 over root 2 and -3 over root 2 are real close to 2. So 3 over root 2, they're just a little bit beyond it. So 3 over root 2 and then 3 and 9/2 is 4.5. So 1, 2, 3, 4.5. Right? And then same over here, -1, -2, -3, -4 and a half. And so those are our absolute max and our absolute min values. And so now we'll go through and we'll find our second derivative. So in order to find our second derivative, we need to go back to our first derivative. Right, and our first derivative, what do we have for our first derivative? F prime of x was equal to 9 minus 2x squared over root 9 minus x squared. So as we look for our second derivative here, f double prime, we'll have to use the quotient rule. So it'll be denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is 1 over 2 root 9 minus x squared, times the derivative of 9 minus x squared, which is negative 2x. And it's all going to be over 9 minus x squared because it's root 9 minus x squared squared. We can do some basic simplification here, the 2's to begin with. Then we want a common denominator of root 9 minus x squared, which is the same as squaring that root 9 minus x squared in the numerator, which is going to end up giving us 9 minus x squared times negative 4x minus 9 minus 2x squared times negative x over 9 minus x squared to the 3/2 power, or 9 minus x squared times root 9 minus x squared, however you prefer to look at it. I'm not worried about that denominator because it's again going to be 3 and negative 3. So really all I care about is my numerator, which I'll simplify that numerator down, right? So if I do all the distributing there, we're going to end up with, let's see, that's a negative 36x from the 9 times the negative 4x, and then a plus 4x cubed from the next term, and then it's going to be a plus 9x, and then it's going to be a minus 2x cubed there at the end. So we want to know, when does that equal 0? Well, that'd be when 2x cubed minus 27x equals 0. We'll factor out the x from it, leaving us with 2x squared minus 27, giving us x equals 0, and x equals plus or minus root 27 over 2. Well, the square root of 9 is 3, right? And so 27 over 2 is more than 9. So these are not in the domain. So we don't have to worry about those. So really we just have a singular possible point of inflection at 0. Right? So we'll do that on the next page. Right? We'll have say f double prime of x equals 0 if x equals 0. Our sign chart with negative 3 and 3 at the endpoints. And if we plug that into, plug values into our second derivative there, the denominator is always going to be a positive, but our numerator, which was 2x cubed minus 27x, if I put something in like 1, I get a negative, but if I put in something like negative 1, I get a positive. And so that tells me that we're going to have a positive value here and a negative value here, telling us we're concave up from negative 3 to 0, concave down from 0 to 3, and then we have a point of inflection at that point 0, 0. So now we're ready to graph. We start out here as decreasing concave up, continue to do that, and then decreasing concave down, hitting our point of inflection at 0, 0. And so that's what our graph looks like. And actually, before we move on with this next one, we were supposed to do the range. We never actually got around to the range of that last one. So the range, right, we could see in our graph that we were going up to 9/2 and down to negative 9/2, right? These 2 points right here. And so our range is just going to be from negative 9/2 to positive 9/2. All right, so now we're ready to move on with sine squared x on the interval from 0 to 2 pi. Now, a couple nice things about this one is there's not going to be any asymptotes. There's certainly no horizontal asymptotes because we have a restriction on the domain. And there's no discontinuities, and it's not a rational function, so there's no vertical or slant asymptotes. So we just have no asymptotes for this in general. We'll set the function equal to 0. So we want to know, when does sine squared x equal to 0 for our x-intercepts? Well, that happens when x is 0 and pi and 2 pi on our interval. So our x-intercepts are going to be 0, 0, pi, 0, and 2 pi, 0. Okay. And then the y-intercept, since we have 0, 0, that's just going to be our y-intercept as well. We don't really need to worry about the domain. We have the domain here. And then the range, we'll figure that out later, but we should know that the range of this, actually, we could do it now if we just think logically about it, right? So we don't forget like we did with the last one. The range is just going to be from 0 up to 1, right? Because the sine function only gives you outputs between -1 and 1. And if I square something between -1 and 1, I'm always going to get a positive number that's between 0 and 1. So our range is just going to be from 0 to 1. So we should see that when we graph it as well. So we'll put on our points here. I'm going to put on 0, 0. Let's see here. We'll make this pi. And we'll make this 2 pi. So we have a point at pi, 0, and at 2 pi, 0. And kind of got those spaced out nicely. Actually, I think what we'll do, actually, instead of spacing them in 6s, just because I kind of have a little bit of an idea of what this is going to look like. Let's see. Let's call this pi over 4, pi over 2. Let's see if we have enough room to do that. We're just a little short over here. So, oh well. We'll get down to 2 pi over there at the end in a little bit. So this will be our pi value, and 2 pi is going to be all the way down here where we have this point here. We're going to have pi over 0 there. Right, so really I don't need this full arrow here. That's going to be 2 pi right there. So now we're ready to take our derivative. So our derivative for sine squared, we'll do that on a new page. So in order to take that derivative, we're going to use the chain rule, right? So that should just be 2 sine x times cosine x, right? So 2 sine to the first times the derivative of sine. We'll set this equal to 0. So we know that this is going to have potential maxima and minima whenever sine is equal to 0 and whenever cosine is equal to 0. Well, that'll be at x equals 0, pi, and 2 pi. And cosine is equal to 0 when x is pi over 2 and 3 pi over 2. Okay? So now we just make a sine chart with all these values, and we would have put 0 and 2 pi on it anyway, because we know that those are our endpoints of our domain here this time. But now we'll just plug some things in. And this should be really easy because between 0 and pi over 2, that's the first quadrant where sine and cosine are both positive. So multiply them together, you get a positive. In the second quadrant, they have opposite signs. Sine is positive and cosine is negative, so you get a negative. In the third quadrant, they're both negative, so multiply them together and you get a positive. And in the fourth quadrant, cosine is positive, but sine is negative, so you get a negative. And so we should see that our function goes from increasing to decreasing to increasing to decreasing. We've already got the values at 0, pi, and 2 pi, so we do need to find f of pi over 2. Well, the sine of pi over 2 is just equal to 1, right? So if I square that, that's going to be 1. And the sine of 3 pi over 2 is equal to -1. So when I square that, I'm just going to also get positive 1. So we are looking at a local max of 1. And it happens to be an absolute max too. Probably didn't ask for it, so I'm not going to bother to write it. That's at x equals pi over 2 and x equals 3 pi over 2. We have a local min of 0, and that's at x equals 0, x equals pi, and x equals 2 pi. Okay. We're increasing from 0 to pi over 2, from pi to 3 pi over 2. And we are decreasing from pi over 2 to pi, and from 3 pi over 2 to 2 pi. And we'll just put on those values onto our graph here. I'll just say, I don't know what we'll do here. We'll just, how high up should we make this? Let's say 6 units up here is 1. So our scale is going to be a little funky here, but at pi over 2, we'll be at 1, and at 3 pi over 2, we'll also be at 1. Now we'll move on to our second derivative. Now, before we do our second derivative, let's think about our first derivative, right? Our first derivative, f prime of x, was 2 sine x cosine x. Now, if I take the derivative of that, that requires the product rule, which is kind of annoying. But I could rewrite it as the sine of 2x using the double angle identity that you should know and have memorized. So now when I take the derivative, it's just an easy chain rule, 2 cosine 2x. And we want to know, when does 2 cosine 2x equal 0? Well, that would be when the angle is equal to, cosine is equal to 0 at both pi over 2 plus 2 pi n, as well as 3 pi over 2 plus 2 pi n, right, where n is any integer. And so we need to solve this, plugging in values of n until we get outside of the interval 0 to 2 pi. So we'll divide everything by 2, giving us x equals pi over 4 plus pi n, and x is equal to 3 pi over 4 plus pi n. When n equals 0, that gives us pi over 4, and it also gives us 3 pi over 4. When n equals 1, we get x equals 5 pi over 4, and x equals 7 pi over 4. And when n equals 2, we go outside the domain, right? Because if we multiply pi n by 2, or pi times 2, and add pi over 4 to it, we're going to be outside of the domain of 0 to 2 pi. So we've got 4 possible points of inflection. We'll make a sign chart with our second derivative, making sure to keep 0 and 2 pi on there. We'll put pi over 4. We'll put 3 pi over 4. We'll put 5 pi over 4. And we'll put 7 pi over 4. And so when we do that, we'll just test some values into our second derivative. Right? If we take something between 0 and pi over 4 and double it, we're still in the first quadrant, right? Which is going to give us a cosine that is positive. If I take something between pi over 4 and 3 pi over 4, right, and double it, right? Let's say we pick pi over 2, right? Pi over 2, we double it, that's pi. The cosine of pi is now negative, so that's going to be a negative. If I take something between 3 pi over 4 and 5 pi over 4, like pi, and double it, that's 2 pi. Cosine of 2 pi is positive. And right on down the line, this is going to be negative and positive. They're going to flip every time. So we're going to have, actually, looks like 4 different points of inflection. But the nice thing here is when I evaluate my function, sine squared of x, right? Sine squared of x, well, the sine of pi over 4, the sine of 3 pi over 4, 5 pi over 4, and 7 pi over 4 are all either positive or negative root 2 over 2. So when I square them, I'm just going to get root 2 or negative root 2 over 2 squared, which is just 2 over 4, which is just 1/2. So we're going to end up with all these points of inflection, right? But they're all just equal to 1/2. So our points of inflection are going to be pi over 4, 1/2, 3 pi over 4, 1/2, 5 pi over 4, 1/2, and 7 pi over 4, 1/2. Right? And lots of different concave up, concave down intervals. We're concave up. We started out concave up, right? So from 0 to pi over 4. And then again, picking back up at 3 pi over 4 to 5 pi over 4. And then picking back up again at 7 pi over 4 to 2 pi. And we were concave down on the interval from pi over 4 to 3 pi over 4. And the interval from 5 pi over 4 to 7 pi over 4. And now we'll plot those points of inflection on our graph. So these are our pi over 4 intervals here. Right? This is pi over 4. And then that's 1/2. And at 3 pi over 4, it's 1/2. and then it's half, and then it's a half. And so we start out concave up, and every time we hit those points at a half, we switch concavity to concave down, or back to concave up, and we hit a minimum, maximum, minimum, maximum, minimum. And that's what our graph of sine squared of x should look like. All right, our next function here is the function x squared e to the negative x. So as we look at x squared e to the negative x, we're definitely going to have to think about some asymptotes this time, potentially. Not guaranteed, but certainly a possibility of some asymptotes. But first we'll start off with just our x and y intercepts here. So we'll set this equal to 0, or that equals 0 when x squared is 0, which would be when x is 0, which means that we've got an x-intercept of 0, 0, which means that our y-intercept is also 0, 0. The e to the negative x part, right, e to the negative x is never equal to 0. In fact, e to the negative x is always a positive number. No matter what you plug into that, when you raise it to a e to a power, you always get something that's positive. Right? So we don't have to worry about e to the x being equal to 0. We should do some limits here to figure out horizontal asymptotes. So a limit as x approaches infinity of f of x is going to be, well, if we think about x squared e to the negative x, right, we could rewrite that as x squared over e to the x, which means we've got infinity over infinity. But the e to the x infinity is faster, which means this trends towards 0. And when we do the limit as x approaches negative infinity of f of x, we end up with negative infinity squared, which is infinity. But then we end up with an e to the negative infinity in the denominator, which should go up to the numerator to become infinity, giving us infinity. So we have a horizontal asymptote of y equals 0 to the right. We have no horizontal asymptote to the left. And there's not going to be a vertical asymptote because this doesn't have any discontinuities. And there's also not going to be a slant asymptote because this is not a rational function. So there's our asymptotes. We can plug any number into this, so our domain should be all real numbers, negative infinity to infinity. And we'll worry about the range when we're done with the problem. So we've already got 1 point, the point 0, 0, so we'll put that on here. And then we'll start off now with working with our derivative. So if f of x is equal to x squared e to the negative x, then f prime will be found using the product rule. X squared times the derivative of e to the negative x, which is negative e to the negative x using the chain rule, and then plus 2x times e to the negative x. We can factor out the x e to the negative x from this. So this becomes x e to the negative x, and we're left with a negative x. And then if we factor that, the x e to the negative x from that, we get plus 2. Okay? This is only equal to 0 if x is equal to 0. E to the negative x is always greater than 0. Or if negative x plus 2 is equal to 0, which would be when x is equal to 2. So we have two possible minima or maxima, x equals 0, x equals 2. We'll make a sign chart with them to determine if they actually are. Remembering that the e to the negative x is always positive, so when I make my sign chart, I can just kind of ignore that term, right? Because it's not going to affect the sign of the derivative. So if I plug in something like 1, x is positive, and negative x plus 2 is negative. So we end up with a, if we plug in something like 1, we end up with a positive 1 times a negative 1 plus 2, which is positive. So we end up with a positive in the middle. If we plug in a negative number, we get a negative for the x, but a positive for negative x plus 2, so that's negative. And if we plug in something like 1,000,000, we get a positive times a negative, which is a negative, which tells us that our function decreases, then increases, and then decreases again. So we have a local minimum at 0, and we have a local maximum at 2. We need the value at 0, which we already have. It was 0. But we do need the value at 2. If you plug in 2 to this, you end up getting 4 over e squared, right back into the original function. And I'll just give you an approximation for that. It's about 0.541, right? So we'll state that we have a local min of 0 at x equals 0, and we have a local max of 4 over e squared at x equals 2. And we are decreasing from negative infinity to 0 and from 2 to infinity. And we are increasing from 0 to 2. And so we'll put on that 0.2, comma 0.541 into our graph. Well, let's see here. Let's just make each 2 boxes 1 again here. So 1, 2, 3, 4. That ought to be hopefully enough here for us. If not, we'll add some more. And at 2, as we just said, it should be about 0.541. So that'd be just above a half. So we've got 1 point on there. And now we will go ahead and work with our second derivative. And so our first derivative was this negative. Well, we'll write it out. It's negative x squared e to the negative x is the first part of it, right? Our first derivative was equal to negative. What do we have? We had negative x squared. Yeah, negative x squared e to the negative x, and then we also had a plus 2x e to the negative x. I guess the factored form would have been better. So let's go back and fix that. Factored form looked nicer there in the end. It was x e to the negative x times negative x plus 2. It's really not all that much better. But what we'll do actually to make it so that we don't have to deal with the product rule twice, we'll just call it x e to the x times negative x squared plus 2x. And that should allow us to do this just with one application here of the chain rule, giving us f double prime of x is equal to the first function, e to the negative x, times the derivative of negative x squared plus 2x, which is negative 2x plus 2, and then plus the derivative negative e to the negative x times negative x squared plus 2x. Right. We can again factor out the e to the negative x from this. So if I take out an e to the negative x, I'm left with negative 2x plus 2 minus a negative x squared plus 2x, which is going to give me e to the negative x times positive x squared, and then let's see, we got a minus 2x, another minus 2x is minus 4x plus 2. And so we will then see when that's equal to 0 and see when it's undefined. It's never undefined. It's equal to 0 when x squared minus 4x plus 2 equals 0. So we'll complete the square with that. We'll subtract the 2 over. We'll add 4 to both sides, right? Because negative 4 over 2 is 2. And when we square it, that gives us 4, which means we want to add 4 here. We'll factor to get x minus 2 squared equals 2. We'll square root to get x minus 2 equals plus or minus root 2, or x is 2 plus or minus root 2. And so we've got 2 possible points of inflection. We'll make a sign chart with them. Here is 2 minus root 2, and here is 2 plus root 2. Something to the left of 2 minus root 2 would be 0. If I plug 0 into my second derivative right here, I get a positive times a positive. If I plug something between 2 minus root 2 and 2 plus root 2 in, like 2, I'm going to end up with a positive times a negative, which is a negative. And if I plug in something real big, like a billion, I'm going to get a positive times a positive. So we can see that we have 2 points of inflection. one at 2 minus root 2 and one at 2 plus root 2. Right. And we are concave up from negative infinity to negative, there's not negative, to 2 minus root 2. And again, from 2 plus root 2 to infinity. And we are concave down from 2 minus root 2 to 2 plus root 2. The points of inflection, those are some really irritating numbers. Right? Our points of inflection ended up being 2 minus root 2. And the arithmetic on this, again, once more, is something I would never make you do on the test. It's 6 minus 4 root 2 times e to the root 2 minus 2. And the other one was 2 plus root 2. And that one would be with 6 plus 4 root 2 times e to the negative 2 minus root 2. Okay, so don't worry about the arithmetic on those. Really annoying. The values there are pretty small values. They actually end up being like around a quarter or so. So when I plot those values, and 2 plus root 2 is about 3.4. 2 minus root 2, let's say, is about 0.6. So I'm going to plot those at, right around here. And also at about, what do we say, 3.4. So that'll be, is a little bit higher on that one. So it's like right about here. And that should be enough to graph this. We know we started out concave up till we decreased to that x-intercept. Then we increased after to the point of inflection, still being concave up. But then after that, we increased, but we're concave down through that maximum. We stayed concave down until we hit that point of inflection, but then we switched to concave up, decreased forever towards our horizontal asymptote to the right of y equals 0. And now that we look at our graph, we can see that our range is from a lowest value of 0, which we do hit at 0, 0, even though we don't hit it at the horizontal asymptote, and it goes up towards infinity. And that is everything for that graph. All right, our next one here is f of x equals x times the natural log of x squared. So first of all, we have to think about the domain. Right? We can take the natural log of anything that's positive. And x squared is always positive or 0. So the only thing that's restricted from the domain of this would be x cannot be 0. In other words, our domain is negative infinity to 0, 0 to infinity, which does introduce the possibility of us having a vertical asymptote there at x equals 0. So we'll have to check on that in a bit here. But we do have our domain. We don't know what our range is going to be yet. We can find our x-intercepts by setting this equal to 0. Right? So if we set this equal to 0, x equals 0, well, we know that does not work, right? Because that's not in our domain. But if we set natural log of x squared equal to 0 and exponentiate both sides, we get x squared equals 1, or x is positive or negative 1. So we do have some x-intercepts here of positive 1 and negative 1. So I'm just going to go out here and just kind of like 5 units out here, make 1 and make negative 1 there. So those are our x-intercepts. They are 1, 0 and negative 1, 0. And as far as a y-intercept goes, we'd have a y-intercept when this function is equal, when we plug in 0. Right? So if I plug in 0, I can't do that because that's not in my domain, so there's no y-intercept. As far as asymptotes, like we said, there might be a vertical asymptote at 0. In fact, we should really kind of consider that, which we'll do in a second. There's no slant asymptote. As far as horizontal asymptotes go, if we look at the limit as x approaches infinity of f of x, that's just infinity. right? Because it's infinity times infinity. And the limit as x approaches negative infinity of f of x, well, that's negative infinity times infinity, which is negative infinity. So we have no horizontal asymptotes. As this thing approaches 0, right? So if we look at a limit as x approaches 0 from the right-hand side of this function, really what we're looking at here is x times the natural log of x squared. Well, that's 0 times the natural log of 0 from the right. And in fact, whether I do this from the minus side or the right or the left, that's going to be 0 times the natural log of 0 from the right, which is 0 times infinity. But then we have to think about what's happening more quickly here. Are we approaching 0 faster with the x, or are we approaching infinity faster, or negative infinity faster, with the natural log of 0? And we know that natural log functions move more slowly than a linear function does. And so what that's actually telling us here is that we are going to be approaching 0 faster than we are approaching negative infinity when I evaluate this function, right? And so this ends up being 0. And so another way we can look at it, if it's, we could like rearrange this and use L'Hopital's rule, but if we just logically think about it, this should just be 0. So we're approaching 0 in the middle here, which means we're actually going to have a hole there at 0, 0. We're not going to have a vertical asymptote. So we have no asymptotes here. So now we're ready to deal with the first derivative. So our function f of x was x ln of x squared. So taking our first derivative here, we're going to use the product rule, which is going to be x times the derivative of natural log of x squared, which is 1 over x squared, times 2x. And then we'll add to that the derivative of x, which is 1, times the natural log of x squared. So that's our first derivative, which simplifies to 2 plus ln of x squared. Well, 2 plus ln of x squared is never going to be undefined except at 0, which we already have dealt with in our graph. So really we just want to know, when does that equal 0? Well, that'd be when the natural log of x squared is equal to negative 2. Okay, so if we exponentiate this again, we get x squared equals e to the negative 2, or 1 over e squared, or we end up with x is equal to positive or negative 1 over root, not root e, just 1 over e, right? Because we're square rooting e squared. So just positive or negative 1 over e. We'll make a sign chart, remembering that we should put 0 on our sign chart also, because weird things can happen at these discontinuities. So we'll do negative 1 over e, 0, and 1 over e, even though 0 is not a critical value. If we plug in something more than 1 over e, like a billion, we get 2 plus a positive, which is positive. And if we put in something like negative a billion, we get 2 plus the natural log of a really big number, which is still going to be positive. If I put in something between 0 and 1 over e, like 1 over 1,000, right? The natural log of 1 over 1,000 squared is a really, really, it's a really small number. It's a really, really big negative. So 2 minus a really big number is going to be negative. The same is going to happen here. So we're going to be increasing, right, from negative infinity to negative 1 over e. And then we're going to be increasing again from 1 over e to infinity. And we're going to be decreasing on negative 1 over e to 0. This time we're going to put the parenthesis there, even though the College Board normally likes brackets, because our function isn't actually defined at 0. And then again from 0 to 1 over e. And we need to plug in 1 over e back into our original function. So if we plug in 1 over e into our original function to find what these actually these maxes and mins are. Or like if I put 1 over e into that, I get, we'll say f of 1 over e, right? That's going to be 1 over e times the natural log of 1 over e squared, or the natural log of e to the negative 2, which just ends up being negative 2 over e, right? Because we'll simplify here. It's negative, it's 1 over e times negative 2, which we can bring out in front, times the natural log of e, right? Because you can bring out the exponents from inside the logarithm. So this is just negative 2 over e. And if we do the same thing with negative 1 over e, I'm not going to write out all the work for that one. It comes out to be just a positive 2 over e because of the difference in the sign there. So we would say, we'll try and I'll write this in a different color so we can kind of see it. We would say we have a local min. Let's see, we were increasing, decreasing, still decreasing, now increasing. A local min of negative 2 over e at x equals 1 over e. And we'll have a local max of 2 over e at x equals negative 1 over e. And now we'll go and we'll plot those points. So 2 over e is like, a little bit less than 1. And 1 over e is, quite a bit less than 1. It's like 1 over 2.7. So that's more like a fifth-ish. So we're going to put these points down here at, negative, like I said, negative 2 over e is going to be a little less than negative 1. So, somewhere around here. And this one over here is going to be kind of more like right around here. And we didn't plot our points at negative 1 and 1, 0. So that's what we've got so far. And now we just need to deal with the second derivative, whether this is concave up or concave down. So our first derivative, f prime, was 2 plus ln of x squared. Our derivative of that, right, is just going to be, well, the derivative of 2 is 0. So we have f double prime of x is just the derivative of natural log of x squared, which is 1 over x squared, times the derivative of x squared, which is 2x, which is just 2 over x. We know that this is never equal to 0. It's undefined when x is 0, which is not in our domain, but we still should make a sign chart with 0 on it to see if it changes from concave up to concave down or vice versa there. So if I plug in something more than 0 into 2 over x, I get a positive, so we're concave up. And something less than it, we are negative, so concave down. It's not a point of inflection because the function isn't defined at 0, but we will say it's concave down from negative infinity to 0 and concave up from 0 to infinity. So we knew that we were going down to negative infinity here. We're going to be concave down until we hit this hole. Then we're going to switch to be concave up and go up towards infinity afterwards and always be concave up. And now we should be able to see that our range goes all the way from negative infinity to infinity. We do have this hole here, but we did hit y equals 0 at a couple other places. So our range is going to be negative infinity to infinity to finish up that problem. All right, our next one here is going to be f of x equals 4x e to the 2x. So for this one, we're going to start off again by just doing what we can do without taking a derivative. So without taking a derivative, we're just going to set it equal to 0. We know that 4x equals 0 when x is 0, which gives us an x-intercept of 0, 0. Which also ends up being our y-intercept. And e to the 2x is always positive. It's never equal to 0. So we're just going to have a singular x-intercept here and a y-intercept of 0, comma, 0. We are then going to look about asymptotes. There's not going to be any vertical asymptotes. There's not going to be any slant asymptotes because this function has no discontinuities and it's not a rational function. But it could have horizontal asymptotes. So we'll look at the limit as x approaches infinity of f of x, which is infinity times infinity, which is infinity. So there's no horizontal asymptote to the right, but if we do the limit as x approaches negative infinity of our function, we end up with negative infinity over infinity faster, right? Because we have 4 times infinity, and then we have e to the negative 2 infinity, which drops to the denominator, and an exponential increases faster than a linear, which gives us 0, which means that y equals 0 is our horizontal asymptote to the left because it's towards negative infinity, and we have no horizontal asymptote to the right. We do know our domain here. Our domain should be all real numbers. Right? Domain will be all real numbers because we can plug anything into this function, so there's no restrictions on the domain. And we will worry about our range, again, like we have with the last few, at the end. So now we are ready to do what we can do with a first derivative. So if f of x is equal to 4x e to the 2x, then our first derivative should just be f prime of x is 4x times the derivative of e to the 2x, which is 2e to the 2x, and then plus the derivative of 4x, which is 4 times e to the 2x. We should be able to factor out the 4e to the 2x from that, leaving us with 2x plus 1. Set that equal to 0. This part's always positive, so we don't need to worry about that. But we do end up with x equals negative 1/2 there. And so we have one possible max or min, which is at negative 1/2. We'll put that on a sign chart for our first derivative. Plug in a positive number like 1,000,000. We end up with a positive times a positive, so we're increasing here. Plug in something like negative 1,000,000, and 4e to the 2x is still positive, but 2x plus 1 is negative. So f decreases, and then it increases. We do need to figure out what f of negative 1/2 is equal to. Now, I'm not going to, I guess I should go through and do that. So 4 times negative 1/2 times e to the 2 times negative 1/2 is just negative 1. So we just end up with negative 2 over e. Okay? So we have a local min of negative 2 over e at x equals negative 1/2. We are decreasing on the interval from negative infinity to negative 1/2. And we are increasing on the interval from negative 1/2 to infinity. And then we will just go right ahead from there and plot that point at negative 1/2. So here's our graph. I'm going to go over here to like make 6 units over here as 1 and negative 1 here. In fact, I'm going to do the same thing down here. That'll be negative 1 and positive 1. And so at negative 1/2, it should be halfway through there, and negative 2 over e, which is still a little less than negative 1, right? We're going to be right around here-ish. So that'll be where we have that local minimum. And then we will go ahead and deal with our second derivative now. Right? So our second derivative will come from using our first derivative, right? F prime of x was equal to 4e to the 2x times 2x plus 1. So our second derivative should be the first function, 4e to the 2x times the derivative of 2x plus 1, which is 2. And then we will add to that the derivative of 4e to the 2x, which is 8e to the 2x times the 2x plus 1. We'll again factor out the common term. This time our common term to factor out is going to be 8e to the 2x, leaving us with 1 plus 2x plus 1, or 8e to the 2x times 2x plus 2. We know that 8e to the 2x is always positive, so we don't have to really worry about that equaling 0. But 2x plus 2 equals 0 when x is negative 1. So we have one possible point of inflection. We'll put it on our sign chart. Plug in something more than that, like 0, and we get a positive for our second derivative. Plug in something less than negative 1, like negative 1,000,000, and we get a negative for our second derivative. So we do have a point of inflection at negative 1. Right? F of negative 1 should be negative 4, because it was 4x, e to the negative 2, or negative 4 over e squared. So our point of inflection is going to be negative 1, negative 4 over e squared. We're going to be concave down on the interval negative infinity to negative 1, and concave up on the interval from negative 1 to infinity. And we'll plot that point negative 4 over e squared, or negative 1 comma negative 4 over e squared. Negative 4 over e squared is even closer to 0. It's more like about a half, or negative a half. So we'll just kind of throw that in right around here. And we know we're concave down and approaching that horizontal asymptote to the left until we get to that point at negative 1. Then we switch at our point of inflection to be concave up. And then after that, we go up, being concave up through our x-intercept and our y-intercept, and go up towards infinity, just like our limit told us that we should over here. Now we should be able to see that our range, right, is going to be from this lowest point. This was an absolute minimum down here. Right? That point's value was negative 2 over e. So our range is going to be negative 2 over e all the way up to infinity. And that is our graph for that function. So our next function here is another exponential function. We got e to the x times x squared minus 2. So once again, the first thing that we'll do is we will do all the things we can do without taking a derivative, which means we'll set it equal to 0. E to the x we know is always greater than 0, so that's never going to equal 0. But x squared minus 2 equals 0 gives us x equals plus or minus root 2. So we have two x-intercepts. They are root 2 comma 0 and negative root 2 comma 0. Does not give us the y-intercept, so we'll need to find our y-intercept. So of course we find our y-intercept by just plugging in 0 to the function, right? F of 0 is e to the 0 times 0 minus 2, which is, well, e to the 0 is 1 times negative 2 is negative 2. So our y-intercept is the point 0, negative 2. Okay, so we'll plot that point on here, and I'm gonna make each 2 boxes 1 this time. So 0, negative 2 ought to be right there, and then root 2, 0. Root 2 is between 1 and 2. It's about 1.4, so there'd be root 2, 0, and it'll be negative root 2 comma 0. So we got our x-intercepts and our y-intercepts on there. If you think about the domain of this function, well, this function can be evaluated at all real numbers. So our domain is going to be negative infinity to infinity. There's no nothing that causes a discontinuity here. We'll deal with the range later once we find maxima and minima and all that stuff. We do need to do asymptotes. Now, there's not going to be any vertical or slant asymptotes, right? So we'll say no vertical asymptotes, no slant asymptotes, because again, there's no discontinuities, which is what would give us a vertical asymptote, and it's not a rational function. That's what would give us a slant asymptote. So really, we just need to find the horizontal asymptote. So we'll do a limit as x approaches infinity of f of x, which in this case just gives us infinity times infinity, which is infinity. So there's no horizontal asymptote to the right. And then as we do the limit as x approaches negative infinity, we should see that that gives us e to the negative infinity times negative infinity squared, or we'll just call it infinity squared, minus 2, still infinity, which of course is infinity over infinity, but the e to the negative infinity that goes to the denominator is faster, which means this equals 0, which means we have y equals 0 as a horizontal asymptote to the left. So that's everything we can do without taking a derivative, and we'll make sure that when we graph this, we remember to put in our horizontal asymptote to the left. In fact, there's our horizontal asymptote to the left. So we'll make sure that we're approaching that as we graph this problem. So next up is to find our derivative. So we'll need a new page for that. Since our original function is f of x equals e to the x times x squared minus 2, we'll take the derivative using the product rule. So f prime of x will be e to the x times the derivative of x squared minus 2, which is 2x, plus the derivative of e to the x, which is just e to the x, times x squared minus 2. We'll factor out the e to the x, leaving us with x squared plus 2x minus 2. And of course, we'll set this equal to 0, realizing that e to the x is always greater than 0, so we don't have to worry about that piece. But when we set x squared plus 2x minus 2 equal to 0, the easiest way to solve that is just to bring the 2 to the other side and complete the square, right? So if we take the 2, that's our b value, divided by 2, that's 1, and then square it, we get 1, right? So we want to add 1 to both sides. So when we factor this, we get x plus 1 squared equals 3, or x plus 1 equals plus or minus root 3, or x equals negative 1 plus or minus root 3. So we have two critical values that we need to put on our sign chart. And we'll do that. Here's negative 1 minus root 3, and here's negative 1 plus root 3. Something between those two things to test into our derivative would be something like negative 1. So really we just care about is x squared plus 2x minus 2 positive or negative at negative 1, because we know e to the x is positive. So if we plug in negative 1 to that, we get negative 1 squared, which is 1, minus 2, which is going to be negative. If we plug in something more than negative 1 plus root 3, like a billion, we clearly get a positive times a positive. And the same when we do a negative a billion, because the negative a billion squared becomes such a large positive that it dominates the rest of it. So our function f goes from increasing to decreasing to increasing, telling us we have a max at negative 1 minus root 3 and a min at negative 1 plus root 3. I'm not going to go through the arithmetic to find these values. I've already done it in advance. So f of negative 1 minus root 3 is just e. I mean, it's just plug it into that. But it does require some simplification, which is kind of annoying. It's e to the negative 1 minus root 3 times 2 plus 2 root 3. And f of negative 1 plus root 3 is just e to the negative 1 plus root 3 times 2 minus 2 root 3. And of course, I'm not going to give you anything that annoying to evaluate on the test, nor would they most likely on the AP test as well. So we'll note that our function is increasing on the interval from negative infinity to negative 1 minus root 3, and again from negative 1 plus root 3 to infinity. It is decreasing on the interval from negative 1 minus root 3 to negative 1 plus root 3. And we have a local max of e to the negative 1 minus root 3 times 2 plus 2 root 3 at x equals negative 1 minus root 3. And we have a local min of, what do we have? We have e to the negative 1 plus root 3 times 2 minus 2 root 3 at x equals negative 1 plus root 3. And so we would just approximate those values to plot those points on our graph. So negative 1 minus root 3 is going to be at negative 2.7. And then that value of e to the negative 1 minus root 3 times 2 plus 2 root 3 is less than 1. In fact, it's even less than half. It's like 0.4-ish, I think. So here at negative 1, negative 2, negative 2.7-ish, we're going to be right around here. And then for the other one, negative 1 plus root 3, that's about 0.7. And the y value there came out to be just right around negative 3, a little less than negative 3. So that'll be, right around there. So we've got our points plotted on there. Now we just need to do our second derivative test. So our first derivative was e to the x times x squared plus 2x minus 2. So if f prime of x is e to the x times x squared plus 2x minus 2, then we'll take our second derivative again using the product rule. So our product rule here is going to give us e to the x times the derivative of x squared plus 2x minus 2, which is 2x plus 2, and then plus e to the x times x squared plus 2x minus 2. We can factor out the e to the x again, which is going to leave us with an x squared, and then a plus 2x and a plus 2x, which is plus 4x, and a plus 2 and a minus 2, which will go away. So we've just got e to the x times x squared plus 4x, or if we want to factor that out further, it's x e to the x times x plus 4. We can see that we get x equals 0 and x equals negative 4 as our possible points of inflection. And of course, e to the x, we know, again, is always greater than 0, so we don't really have to worry about that. So we'll make our sign chart for our second derivative using negative 4 and 0 on it. And if we plug in something more than 0, like a billion, all three of these terms are positive, so we're concave up. If we plug in something like negative 2, that's between negative 4 and 0, the x is negative, but e to the x and x plus 4 are both positive, so we're negative on that interval for our second derivative, which means the function is concave down. And then if we plug in something like negative 4 into each of these three pieces, we get a negative times a positive. Something less than negative 4 times another negative gives us two negatives times a positive, which is a positive. We've already got the value at 0. We already found that value. It was, I believe the original function made it negative 2. No, yeah, negative 2. And so all we need to do is find f of negative 4 now to find our second point of inflection, because we clearly have 2 points of inflection, because it does change from concave up to concave down and then back again. So in the original function, if you plug in negative 4, you get 14 times e to the negative 4, right? So that'd be 14 over e to the 4th. And so we'll write out our points of inflection. We have 2 points of inflection. One of them is negative 4 and 14 over e to the 4th. And the other one is just that point 0, negative 2 that we already found as our y-intercept. We'll state that we are concave up on the interval from negative infinity to negative 4, and again from 0 to infinity, and that we are concave down on the interval from negative 4 to 0. And to figure out what 14 over e to the 4th is, we just use our calculator to figure that out. 14 over e to the 4th is about a quarter. It's about 0.256. So at negative 4, we want to have a point at about a quarter. So here's negative 4, and we'll put that point there at about a quarter. In fact, that was a little bit lower than I should have, maybe. But maybe right about there is where it should be. So now we're ready to sketch our graph. Our graph starts out as concave up according to our second derivative sign chart till we get to negative 4. Then it's always concave down till 0. when it flips back to concave up. But we are increasing until we get to -1 minus root 3. Then we decrease to -1 plus root 3. So we're going to start out as concave up, approaching that asymptote. We switch to concave down. We continue being concave down until this point of inflection at 0, -3, or sorry, 0, -2. We switch to concave up. We stay concave up until we hit that minimum and continue increasing afterwards. And so that's what our graph should look like. And then for our range, now we can see what our graph actually looks like. We have an absolute minimum there at this point down here, right? And so that absolute minimum was the somewhat annoying value of, write it in here. It was e to the -1 plus root 3 times 2 minus 2 root 3. And then our range continues all the way up forever to infinity. All right, this is our last graph here that we're doing on this functions to graph assignment. So same process that we've been using. We are first going to do everything we can do without taking a derivative. So we will set this equal to 0. We know that e to the x is always greater than 0, so we don't have to worry about that. But x cubed minus 4 equals 0 gives us x equals the cube root of 4. So we have an x-intercept that is the cube root of 4, comma 0. And so we'll just plot that, right? The cube root of 4 is between 1 and 2. So let's see, how much do we want to space this out this time? I think we're just going to make each box 1 for everything. So there will be our cube root of 4, comma 0. We'll find our y-intercept by finding f of 0, which would be e to the 0 times 0 minus 4. So we're going to end up with a y-intercept of -4, because e to the 0 is 1. 1 times -4 is -4. So our y-intercept is the point 0, -4. So that'll be right here. And then we'll need to think about the asymptotes. Once again, we're not going to have any slant asymptotes because this is not a rational function. We're not going to have any vertical asymptotes because there's no discontinuities on this function, which tells us our domain. Our domain is -infinity to infinity because there's nothing that would cause a restriction on the domain here. So then we just need to do our limits. A limit as x approaches infinity of this function is just going to be infinity times infinity again, like it was with the last one. So we have no horizontal asymptote to the right. But just like the last one, when I do the limit as x approaches -infinity, then we end up getting an asymptote. Right? We end up with e to the -infinity times -infinity cubed, which is just -infinity, right? But e to the -infinity drops to the denominator, so we have -infinity over e to the infinity, which is 0 because e to the infinity increases more quickly. So we do have a horizontal asymptote of y equals 0 to the left, just like we did with the last one. So we'll sketch that in there too. There's our horizontal asymptote of y equals 0 going to the left. And once again, just like with the last one, we'll deal with our range at the very end once we actually have a sketch of our graph. So next step is to find your derivative. So f of x was e to the x times x cubed minus 4. Tells me that f prime of x is equal to e to the x times the derivative of x cubed minus 4, which is 3x squared, plus the derivative of e to the x times x cubed minus 4. Right? This is our product rule. We'll factor out the e to the x, leaving us with x cubed plus 3x squared minus 4. And then we'll need to factor that out. So if we don't know how that factors, we have to use the rational root theorem to figure out the possible rational roots. So we always take the factors of the constant term, which are 1, 2, and 4, positive or negative, and divide them by the factors of the leading coefficient, which is just 1. So the only possible rational roots of this are the quotient of each of these three things, 1 over 1, 2 over 1, and 4 over 1. So it's either positive or negative 1, positive or negative 2, and positive or negative 4. Now I think if we just look at this and think about those values, we can see that if we plugged in 1 to this, right, 1 plus 3 minus 4 would be 0. So 1 seems like it'll work. So if we do synthetic division with this, using 1 up in the box for a factor of x minus 1, we can put 1, 3, 0 for 0x, and negative 4 going across as our coefficients, and figure out what we get if we divide it by x minus 1. So we drop the first one below, multiply by what's in the box. 1 times 1 is 1. Then we add 3 and 1 to get 4, multiply the 4 by the 1 that's in the box, add the 0 and 4, multiply that 4 by the 1 that's in the box, and add. And so we see that this ends up factoring to e to the x times x minus 1 times 1x squared plus 4x plus 4, right? And of course, x squared plus 4x plus 4 factors a little bit more into x plus 2 squared. So when we set this equal to 0, we're going to get nothing for e to the x because that's always greater than 0, but we'll get x equals 1 and x equals negative 2 as possible maxima or minima. Now, we should already be clued into the fact that the one at negative 2 is not going to be a max or a min, but we still want to put it on our sign chart just to look at it. Right? We know that one's not going to be because the multiplicity of that root is even, right? It's x plus 2 squared, which tells us that there's not going to be a sign change at negative 2. But we'll see that when we test it out. So if I pick something between negative 2 and 1, that'd be 0, right? E to the x is positive, 0 minus 1 is negative, and 0 plus 2 squared is positive. So we end up with a negative on that range, or on that interval. If we put in something less than negative 2, like negative 1,000,000, e to the x is always positive, but x minus 1 will still be negative, and negative 1,000,000 plus 2 is a big negative, but when you square it, it becomes positive. So we just have a positive times a negative times a positive, which is still negative. And we can see that there is no sign change at negative 2, just like we predicted. If we plug in something more than 1, like 1,000,000, we end up with all three of those terms being positive, so the function increases. So we could say that f is decreasing, and then f is increasing. So we do need to find the values here of f of negative 2 and f of 1, just so we've got those to plot on our graph. And so our original function was e to the x times x cubed minus 4. So if I plug in negative 2 to that, negative 2 cubed is negative 8 minus 4 is negative 12. So this is negative 12 e to the negative 2, or negative 12 over e squared if you prefer. And if I plug in 1, 1 cubed is 1, minus 4 is negative 3. So we have negative 3 times e to the first, or negative 3e. And I'm not actually sure. There's no reason for me to actually find this. I didn't really need this value, right? I forgot that we didn't actually have a minimum or a maximum of negative 2, so we're not really going to plot that point. If you want to plot the point negative 12 over e squared, go ahead. But it's not a min or a max. So we'll state that we have a local min, which we might find out, in fact, we will find out that this is also an absolute min, but the problem didn't ask us for that this time, so no big deal. It's a local min of negative 3e at x equals 1. So we need to plot that. And we are decreasing from negative infinity to 1, and we are increasing from 1 to infinity. So we'll plot the point 1 and negative 3e. So negative 3e, well, e is 2.7128. That's about negative 8, just a little beyond negative 8 if we multiply that by negative 3. So it was at x equals 1, we'll be at negative little below -8. Right? And that's the only point we've got to plot for that one. And now we will move on to our second derivative. Right, so our first derivative was e to the x times x cubed plus 3x squared minus 4. So we'll use the product rule again to find our second derivative. E to the x times the derivative of that polynomial, 3x squared plus 6x, plus e to the x times that polynomial, right? Because the e to the x is the derivative of e to the x. When we factor out the e to the x this time, we get e to the x times x cubed plus 6x squared plus 6x minus 4. And we need to figure out a way to factor this. So again, we'll use the rational root theorem to figure out what the possible rational roots of this might be. Right? It's positive or -1, positive or -2, and positive or -4 from the factors of the constant. And then we divide it by the factors of the leading coefficient, which is still 1. So our options are 1, 2, and 4, both positive or negative of each of them, for where we might have points of inflection. I already know what the value is going to be, so we're going to pick the correct value to start our synthetic division with. But you would just test 1, -1, 2, -2, 4, and -4 in any order you picked. I'd probably not start with 1 just because I'd look at this and say 1 plus 6 plus 6 minus 4 is not 0, right? So I'd probably start with either -1 or 2 if I was just kind of guessing, but I happen to know that the answer here is -2. So I'm going to put -2 in my box, putting my coefficients going across as 1, 6, 6, and -4. And when I do the synthetic division, we'll bring down the 1, multiply it by what's in the box, add the two numbers, 6 to -2 is 4, multiply it by what's in the box, add the two numbers to get -2, multiply the two -2's together to get 4, and we get 0, which is what we want to show that it factored using, in this case, x plus 2 as a factor, right? Because -2 is the root, so x plus 2 is the factor. So we have x plus 2 times what's left, which was x squared plus 4x minus 2, right? So 1x squared plus 4x and minus 2 from the values we got with our synthetic division. X squared plus 4x minus 2 does not factor nicely. So we know we're going to get nothing from the e to the x. We know we're going to get x equals -2 from the x plus 2. And when we set this equal to 0, the x squared plus 4x minus 2, the quickest way to solve that is to bring that 2 to the other side, I think, and complete the square. Right? So once again, when we complete the square, we take half of that 4, which is 2, and square it, which is 4. So we'll add 4 to both sides. We're just making that thing on the left a perfect square trinomial, right? We're making it factor to x plus 2 squared. So we have x plus 2 squared is equal to 6. We'll square root to get x plus 2 equals plus or minus root 6, and x equals -2 plus or minus root 6. Right? And so we have 3 possible points of inflection at -2, and then at -2 plus root 6, and at -2 minus root 6. So we'll make a sign chart for those. So here's -2 in the middle, here's -2 plus root 6, and here's -2 minus root 6. Now we should be pretty positive that this is going to change signs each time because the multiplicity on these roots was all 1. But we'll confirm just to make sure. If I put in something more than -2 plus root 6, like a billion, e to the x is always positive, and then that's positive, and the billion squared dominates, that's positive. So over here we're concave up. If we put in something like -1 billion, we're going to have a negative here, but a positive here, right? Because the x squared dominates, so that's going to give us a negative. And if I put in something between -2 and -2 plus root 6, for example, if we put in -1, let's say, or even better than that, if we put in 0, right? 0 is between -2 and -2 plus root 6. we'll end up with a positive times a negative, right? This will be positive and this will be negative if x is 0. So that'll be negative. And if I put in something like negative 3, which is between negative 2 minus root 6 and negative 2, we end up with a negative from x plus 2, and also a negative from x squared plus 4x minus 2. Two negatives multiplied together make a positive. So we've got our sign chart for our second derivative. We have 3 changes in the concavity of this function, which means we have 3 different points of inflection. And so I'm not going to go through, oh, and here's that point we found earlier. Actually, it was x equals negative 2 with negative 12 over e squared, right? Was the point we found previously. So we're going to write all this out on the next page. So our points of inflection, which there are 3, are negative 2. And when we plugged that in earlier, we got negative 12 over e squared. This time we'll actually use that. For the other 2, I'm not going to go through the process of like simplifying all this down because it's just a pain. So one of those points of inflections is negative 2 plus root 6, and it's goes with e to the negative 2 plus root 6 because it was e to the x times it was just x cubed, so negative 2 plus root 6 cubed minus 4. So that's our point of inflection. And then we have negative 2 minus root 6, and we have e to the negative 2 minus root 6 times negative 2 minus root 6 cubed minus 4, which, those are some kind of annoying values. I wouldn't give you those values on the test, but for our purposes for now, they're just fine. We are concave up. If we look back at our chart, right, we were concave up on the negative 2 minus root 6 to negative 2 and negative 2 plus root 6 to infinity. So negative 2 minus root 6 to negative 2 and negative 2 plus root 6 to infinity. And we are concave down on the other intervals, which were negative infinity to negative 2 minus root 6 and negative 2 to negative 2 plus root 6. We'll plot all these values on our graph. So negative 2 plus root 6 is about negative 6. Negative 2 negative 2 minus root 6 is about negative 4. And when we plugged in that really annoying value, we got about negative 1. So we're going to have a point that's around negative 4, just a little past negative 4, and right around negative 1. So negative 4, negative 1, so right about there. And then when we did negative 2 plus root 6, negative 2 plus root 6 is between 0 and 1. And the value we got when we plugged that in was about negative 6. So we're going to have something that's between 0 and 1 and down to about negative 6. So negative 4, negative 5, negative 6. So right around there. And so those are our points. We still need the negative 2. Oh yeah, the negative 2 and negative 12 over e squared. So negative 2 would be right here, right? Negative 2. And negative 12 over e squared is between negative 1 and negative 2. So right around there. And so we only have the one minimum, right, where we change from increasing to decreasing. Everything else on here, except for that 0, negative 4 point, was a change in the concavity of the function as a point of inflection. So we started out concave down, right? If we look at our chart, we started out concave down, then we switched to concave up, then to concave down, then to concave up. So we'll do our best to sketch this. We're approaching our asymptote, we're concave down, then we're concave up, right? Then we're concave down, then we're concave up again, and then we go back up and increase through our other x-intercept, and that is what our function looks like, right? So we had a point of inflection. In fact, we'll just do this. We had a point of inflection here, we had a point of inflection here, and we had a point of inflection there. And our minimum was there at negative 3e, and it looks like that's an absolute minimum. So when we write out our range, we'll say that our range is from negative 3e up to infinity. And that is the
last graph on our functions to graph homework assignment. That is the end of the walkthrough for this one.